Hello students, welcome to Educate. Today we are going to start with chapter number 11 of physics class 11th, that is thermodynamics. So we are going to see some basic laws. So in thermodynamics we will study zeroth law, first law and second law. So before that, let's see its basic concepts like thermal equilibrium. What does this mean? If there are two objects, suppose this is object A, this is object B, and if they are connected by a conducting wire or if they come into contact and there is no heat flow from A to B or B to A, in that case, we say that A and B are in thermal equilibrium, right? So we can also say that if they are in thermal equilibrium, it means they must have same temperature. So from here, we are able to predict that if body A and body B and body C are taken in such a way that body A is in thermal equilibrium with body B and body B is in thermal equilibrium with body C, then body A will also be in thermal equilibrium with the body C. So this is called zeroth law of thermodynamics. Right. Now, with the help of knowledge so gained, we can study other related facts. So here two types of processes we will see. One is adiabatic in which there are going to be heat exchange, and there will be another process that is isothermal in which heat exchange is possible. So their equations of state can be written as this is PV equal to constant, and equation of state for adiabatic process is PV power gamma equal to constant. What is gamma? If you remember, there are two types of specific heats. One is at constant pressure Cp, another is Cv. If we find the ratio of these two specific heats, so we get gamma. So gamma equal to Cp upon Cv. Now we have understood what is thermal equilibrium and the zeroth law of thermodynamics. Now we are going to see another concept, that is first law of thermodynamics. Right. So here what happens? Heat absorbed is equal to change in internal energy plus work done. Right. So now if we denote heat absorbed as dq and change in internal energy as du and work is w, but w is equal to pdv, pressure into change in volume. So we can say dq equal to du plus pdv. So this is first law of thermodynamics, right? Now here, if there is no change in internal energy, then what will happen? So if du equal to 0, when du equal to 0, then entire energy absorbed will be used up in doing work W, which is PdV, right? So I think this is clear. Now we are going to see different type of heat capacities that we have already studied. The basic formula that we have studied in thermodynamics, not in thermodynamics, in previous chapter, in calorimetry. So we know delta Q, or we can write dq equal to ms dt, mass specific heat, and this is temperature change, or we can also write it delta Q equal to ms delta t, right? Now when m is 1 gram, then this formula will change to, if m equal to 1 gram, then this formula will become delta Q equal to S delta T, right? Up to here there is no problem. If we take 1 mole, then S, if substance is 1 mole, in that case heat capacity will be written as C. So delta Q equal to, in place of S we will write C, right? So C into delta T, or this can further be written as, here S is equal to how much? We were taking 1 gram and then we are dividing by mole, 1 mole. So in that case our relation will become C equal to, here we can write as mu. So for this delta Q equal to, we take mu times delta T, right? Mass is 1 mole. So here, and we have left C. So if we want to find out C, then what will be the expression? It will be 1 upon mu times delta Q by delta T. Delta Q by delta T, right? So this is the expression. Now we are going to see next thing. Here one more concept is there. These are basic concepts. Now we are going to prove C equal to 3R for a solid. So we are considering if a solid of an atom vibrates, if a solid of capital N atoms vibrates in one dimension, then what happens? Then its energy, then we can say it is oscillator, then an oscillator in one dimension will have energy twice of half kBT. Do you remember? This is from principle of equipartition of energy. Each degree of freedom has energy that is half kBT. So this will become kBT, where K is, this kB is Boltzmann constant, right? So if three dimensions are taken in case of three dimensions, so what will happen? So total energy will become how much? It will be, so energy will be equal to 3 kBT. Now, if we take 1 mole, so for 1 mole substance, it will become how much? Energy will be equal to, we will multiply by Na, 3 Na times kBT. But NaKB gives gas constant. So 3 RT, right? So this is energy. Now, if we write, so we can say here our purpose is to find C, and generally this is internal energy. We can say, if we write it as du equal to 3 RT, right? And we find du upon dt. So du upon dt means differentiation of this, so that will be 3R. So, and this is equal to C, specific heat. So we have got the result. Now next point we are going to see. So next point is now we are going to see the relation, Mayer's relation, Cp minus Cv equal to R. So let's prove it. So you know Cp and Cv. So Cp means what? Cp is specific heat at constant pressure, and Cv means specific heat at constant volume. So we are going to make use of first law of thermodynamics. From there we will derive the relations for these, and then finally we will arrive here. So we write the relation delta Q equal to delta U plus P delta V, right? So this is first law of thermodynamics. Now, if volume is constant, at constant volume, what will happen? This delta V equal to, means change in volume will be 0. If change in volume will be 0, then we will get delta Q equal to delta U. Now, we find a change with temperature. So we write delta Q divided by delta T equal to delta U by delta T, right? And this is equal to Cv, right? Now we are going to see what is Cp. So Cp. So for this again we start from here, but this time change in volume will not be 0. So delta Q equal to delta U plus P delta V, right? So here what will happen if we divide each term by delta T? So delta Q divided by delta T equal to delta U divided by delta T plus P delta V divided by delta T, right? Up to here there is no problem. So this will be written as Cp, And we have already proved that this du delta u upon delta t is CV and plus P delta V divided by delta T. Right. But from formula PV equal to RT, if we find the change, here pressure is constant, so P delta V is equal to R delta T. Right. Here we have delta V upon delta T. So if we write delta V upon delta T, what do we get? Delta V upon delta T. It will become R upon P. Alright. So if that value we put here, so we will get CV plus P into R upon P. So PP will cancel out and we will be left with CP equal to CV plus R. So this is basic relation which gives CP minus CB equal to R. I think thing is clear. Now we are going to see next point. Next point is isothermal process. Isothermal process. So here we will try to find out the expression for work done by isothermal process. So we consider a box in which this is position of piston initially and now it moves to this point, and here this is position of piston and this distance say dx and the area of piston is say A. So work done will be area into distance moved, so that is A dx. So let's see what all is happening, and since this process is isothermal, it means its temperature will remain constant. So here we assume pressure of the gas. Let pressure of the gas is P and its temperature is T, and area of cross section is A. Then volume, if we find, so small volume, so that will be equal to A dx, right? Now here initially its situation is when it is pulled upward, in that case pressure will decrease or pressure will change, temperature remaining same. So initial position is P1 V1 V1. It means initial pressure is P1 and volume is V1, and the final position is P2 V2, right? So it means volume is changing, pressure is also changing. So we have to find out work done. So we can write the formula work done by isothermal process. So here what is happening, volume is changing from V1 to V2 and P dV, isn't it? Because work done W dW equal to how much? PdV, change in volume times pressure. Now what can we do further? So here we can write the equation of state since process is isothermal. So equation of state for isothermal process PV equal to nRT, right? Here n is constant, R is constant, T is constant. Here we have P, so we can write P equals how much? P will become nRT divided by V, right? We write this value here. So W isothermal equal to how much? Integration V1 to V2. In place of P, we are going to write nRT divided by V and dV, right? Now integration, if you remember, integration dx upon x gives log x. Here log has base e, that is also written as ln x, right? So log base ex equal to log ln x. So here we can write W isothermal is equal to nRT ln and then ln and here differentiation ln v and limits v1 to v2, right? So this will become nRT ln and then if you remember the property of log, so log x minus log y is equal to log x upon y. So that property we can apply here, nRT log v2 minus log v1 and this will become nRT times this ln and v2 upon v1, right? Now suppose we want to change this ln to log, so there is a relation ln x is equal to 2.32. So ln x equal to 2.302 or 303 x. So we can change it. So it will become 2.303 nRT log v2 upon v1, right? So this is work done by isothermal process. I think you have understood. Now we are going to see work done by adiabatic process. So in case of adiabatic process, what happens? So work done by adiabatic process. Here Adiabatic process means here we are doing adiabatic expansion. So initially gas is up to here and now it moves through distance dx and piston has area A. So volume change will be A dx, and equation of state of adiabatic process is PV power gamma equal to K. Right. So this time again we will use the same process work done as we have done in previous case, that volume changes from V1 to V2. Everything will be there except the equation used will be this. So we can say here states, so initial state is P1 V1 T1 and final state will be P2 V2 and T2. It means temperature will also change. So work done W adiabatic is equal to V1 to V2 and same concept PdX. Right. Now we have to put, sorry, not PDX, if you remember, work done is PdV. So PdV we put here, and then value of P from this equation of state we are going to put. So P equal to K divided by V power gamma, right? So here we write integration of V1 to V2. In place of we write K V power gamma and dV. Now, this can be further written as work done by adiabatic is equal to integration V1 to V2, and here K times V power minus gamma and dV, right? And you remember integration x power n dx becomes x power n plus 1 upon n plus 1, provided n does not equal to minus 1. So same rule we apply here. So it will become how much? It will become k v power minus gamma plus 1 divided by minus gamma plus 1, right, with limits v1 to v2. Up to here, is there any problem? No. So we can further write w equal to w adiabatic is equal to, here we can write this as 1 minus gamma. So 1 upon, here k also can be taken common, k upon 1 minus gamma, and then inside what is there? Here we write V2 power minus gamma plus 1. So minus gamma plus 1, and then minus V1 minus gamma plus 1, right? Or we can write it as 1 minus gamma, 1 minus gamma, there is no problem. Now one more concept we are going to make use, since PV power gamma equal to K. So we can convert this PV as per our need. For this we can write it as P2 V2 power gamma equal to K for this, and for this we can make it like P1 V1 power gamma equal to K, right? because here k will get multiplied to this, k will multiply to this. So we will get 1 upon 1 minus gamma times, in place of k means we are going to write P2 V2, right? Then V2 power minus gamma plus 1 minus, for this we write P1 V1. What is missing? Here in place of P2 V2 power gamma, P1 V1 power gamma, then V1 power minus gamma plus 1, right? Let's simplify. So we will be left with 1 upon 1 minus gamma. This is P2 V2. Why? Because power is here, this plus gamma is minus gamma plus 1, and after adding we will get just power 1 minus P1 and B1, right? So we have got this relation, and PV equal to nRT we can apply. So here P2 V2 will become nRT2. So we can write it like 1 upon 1 minus gamma nRT2 minus nRT1, right? So nR can be taken common. So nR divided by 1 minus gamma T2 minus T1, right? So this is work done by adiabatic process. Now here, from here we can conclude, we can give some conclusions, like when work is done by the gas during adiabatic expansion, then work done will be positive, that is T1 will be greater than T2, right? And if, what does this mean? T1 is greater than T2. It means temperature is decreasing, and if work done is on the gas during adiabatic compression, in that case this work done will be negative, and in that case T2 will be greater than T1, which means temperature of the gas rises. And now we are going to see some more processes like isochoric process. What does this mean? Isochoric process means volume is not changing. If volume is not changing, then what change will occur in first law of thermodynamics? If you remember, in first law of thermodynamics, the process involved is, so in this lecture I would like to stop here. Thank you, team education.